Let's continue on with our discussion of partial fraction decomposition by looking at a situation where f of s has an irreducible quadratic term in the denominator. So this is a term that cannot factor or will factor only with complex numbers. To determine what the factors are, let's just look at the quadratic formula where we have the values of s that, or to find the roots of s, we go s is equal to negative b, which is negative 6, plus or minus the square root of b squared, minus 4 times a, which is 1, times c, which is 25, all divided by 2 times a, which is 1. So when you go through and evaluate that, you get the two values of s being s equals negative 3 plus j4, which we're going to refer to the positive root because it results from taking the positive sign here. And then we'll also have s equaling negative 3 minus j4. Now the factors associated with that are found by setting or subtracting negative 3 plus j4 from both sides. And when you do that, this positive root gives us this factor here, and this negative root here gives us this factor there. So with this broken down or factored into complex numbers, we're now ready to go ahead and write the partial fraction expansion of this. And we can say then that this term here is equal to, let's do it on down here, is equal to k1 over s plus 6 plus k2 over s plus 3 minus j4 plus k3 over s plus 3 plus j4. Once again, we're going to refer to this factor here as the factor associated with the positive root, and we're going to see later on that that becomes significant. So, first of all, as we've done in the past, to evaluate k1, we're going to multiply both sides of this equation by s plus 6. And then we'll evaluate it at s equals minus 6. So on this left-hand side, let's just write s plus 6 times f of s. And then evaluate it at s equals minus 6. Then over here, we multiply each one of these terms by s minus 6. This first term, when we multiply it by s plus 6, the two terms cancel, and we're left only with k1. So we'll have k1. Now here we're going to have plus k2 times s plus 6 over s plus 3 minus j4. Here we'll have plus k3 times s plus 6 over s plus 3 plus j4. Now when we evaluate both of these two terms at s equals negative 6, those terms go to 0. And we're left with s plus 6 times f of s evaluated at s equals negative 6. We need to go ahead and write that. We have then, putting it in here, we'll have 100 times negative 6 plus 3 divided by negative 6. Well, let's see, we've multiplied both sides by that, so that cancels that term there. And then in the quadratic term, we have negative 6 squared plus 6 times negative 6 plus 25. And when you evaluate that, this here, we find that k1, so this is equal to k1, and evaluating that gives us that k1 is equal to negative 12. Now to evaluate k2, we're going to multiply both sides of this equation here, this and this, by the factor s plus 3 minus j4, and then evaluate both sides at s equals minus 3 plus j4. So we have s plus 3 minus j4 times f of s evaluated at s equals minus 3 plus j4. Going ahead and evaluating that here, this side of the equation, we've got this times this, so that factor is going to cancel in we'll cancel that, and we're left with, in the numerator, 100 times s, but s is equal to negative 3 plus j4, and then we have the plus 3. Down below here, we have s plus 6, so that's negative 3 plus j4 plus 6. This term canceled, and then we're left with s, which is negative 3 plus j4, plugging in there, negative 3 plus j4 plus 3 plus j4 on the left-hand side here. And then on the right-hand side, rather than taking the time to write everything, hopefully we understand that when we multiply this side of the equation here by that factor s plus 3 minus j4, we'll have a term here and a term here, but on this middle one, the multiplying this times this term here, they're going to cancel, and it's going to leave us k2 all alone, because when we multiply this term by the s plus 3 minus j4, and then evaluate it at s equals negative 3 plus j4, this term is going to go to 0, and similarly, this term will go to 0. So we get that k2 then is equal to this, which when we evaluate that, we get that k2 is equal to 6 minus j8, or we can write that in polar form as 10 angle negative 53.13, which is, we can write that then as also in exponential form 10 e to the minus j 53.13. So we have a magnitude of k2 here of 10 and a phase of k2 equaling negative 53.13. We're going to need that when we come back here, when we get just a little bit further along. So now, let's go ahead and evaluate k3 by doing the same kind of a thing. We're going to now multiply f of s by the other factor, s plus 3 plus j4 times f of s. And this time we'll evaluate it at s equals negative 3 minus j4. And when we do that, the s plus 3 plus j4 term will cancel, and we're left then with, in the numerator, 100 times s, but s is negative 3 minus j4 plus 3 divided by s plus 6, that's negative 3 minus j4 plus 6, times, now this second term is still there, s, which is negative 3 minus j4 plus 3 minus j4, and then this term again is canceled. And without going through all the details on the right-hand side here, let's just realize that on the right-hand side, the only thing that is left standing is k3. And when we evaluate k3, we get that k3 is equal to 6 plus j8. And we notice that k3 is just the conjugate of k2. In polar form, that then is equal to 10 angle positive 53.13. And in exponential form, that's equal to 10 e to the plus j 53.13. So as conjugates then, the magnitude of k2 equals the magnitude of k3 equals 10, and the phase of k3 is equal to the opposite of the phase of k2. The phase of k2 is a negative 53.13, and the phase of k3 is a positive 51.13. So we now can write the partial fraction expansion for f of s. We've got then that f of s is equal to negative 12 over s plus 6 plus K1 10e to the minus 50 minus j 53.13 over s plus 3 minus j4 plus k3, which was 10e to the positive j 53.13 divided by s plus 3 plus j4. I've gone ahead and rewritten our expanded form here, and we're now ready to transform these individual fractions back into the time domain. Going to the tables, we will remind ourselves that fractions of the form k over s plus a correspond to time domain functions of k e to the minus at. So this first one here, pretty straightforward in the time domain. This then goes to negative 12 e to the minus 6t plus this term here, there's k, so it will be 10 e to the minus j 53.13. Then we have e to the minus a. Well, a here is 3 minus j4, so let's go minus 3 minus j4 times t. So what's doing e to the minus at, e to the minus a times t for this second term. And then we have the third term plus k, which is 10 e to the positive j 53.13 e to the minus a. Well, in this case, a is 3 plus j4 e to the minus a t. And all of this then is multiplied by the unit step function to point out that, again, it's just starting at t equals 0. Now, let's turn our attention to these two terms with the complex exponentials. And let's start by breaking out each of these two terms where we have the sum of exponents there. Let's just use the product rule of exponents to break those apart. So we're going to have 10e to the minus j 53.13. Then I've got multiplying that e to the minus 3t, and then multiplying that we have e to the minus times a minus is a plus j4t. Similarly over here we're going to have 10e to the positive j 53.13, and then we've got an e to the minus 3t and an e to the minus j4t. Now we'll combine the two complex exponentials here and over here, or factor this, rewriting this, then we have 10 e to the minus 3t times e to the j 4t minus 53.13 degrees. And on over here we have 10 e to the minus 3t from here. And then we have e to the minus, minus j times a positive 4t minus j 53.13. You do well maybe to stop the video for just a second and look at what we've done in combining terms. Note the differences in signs, and that by having here we've got j times 4t minus 53.13. Here by factoring out the minus sign we end up with this same 4t minus j 53. But we've got a positive j and a minus j there. So now, continuing on with this, let's note that there's a 10e to the minus 3t term on both of those that we're going to factor out. 10e to the minus 3t times now this term, e to the j 4t minus 53.13 plus, we factored out the 10 e to the minus 3t, plus e to the minus j 4t minus j 53.13 degrees. Now, we look at these two terms here, and we recognize that that's equal to 2 times the cosine, just Euler's formula. This is 2 times the cosine of 4t minus 53.13 degrees. And we've got the 10 e to the minus 3t multiplying that, 10 e to the minus 3t multiplying that, and then we still have over here this term which is just getting carried down, negative 12 e to the minus 6t, all that times u of t. Once again, this would be a good place to stop the video and just look at what's going on. Going from here to here, I used Euler's formula in the form that e to the j theta plus e to the minus j theta over 2 is equal to the cosine of theta. So again, stop the video, but look at this. We have e to the plus j times something plus e to the minus j times something. So this then represents 2 times the cosine of 4t minus 53.13 degrees. This then is the function f of t. That's what we started out to get when we started over with that original f of s. So here's that original f of s, which we factored, and then let's just recap what we've done here. Put it all on one page. This then went to a minus 12 over s plus 6 plus 10 e to the minus j 53.13 over s plus 3 minus j4 plus 10 e to the positive j 53.13 over s plus 3 plus j4. So that was our partial fraction expansion, and we then went through and took it back into the time domain. In the time domain, we found then that f of t was equal to negative 12 e to the minus 6t, and then we saw that these two terms combined into a single term of 2 times 10 e to the minus 3t cosine of 4t minus 53.13 degrees. Now what we want to do is we want to look at this and see where each of these constants came from. Because what we're going to find is that if you can get it into this form, we can identify where these constants end up in the time domain, and we don't have to go through those intermediate steps. So, let's see, that's a minus sign. Let's look here first. Let's note that the magnitude of K1, or of K2 rather, equaled the magnitude of K3, which equaled 10. So this value right here, that 10, was simply the magnitude of both K2 and K3. Now, we'll notice this phase term here, 53.13. That phase term is the phase of K2. Notice the sign on K2 is minus, and the sign down here turns out to be minus sign there also. So this term right here is just the K values. This term right here is the angle associated with K2. Now, the 3, the real part of the factor here, ended up as a minus 3 here. And finally, the conjugate term, or the imaginary part, this 4, ended up as the frequency of oscillation here. So let's look at this. These two terms can be written as magnitude of K e to the j theta over s plus alpha minus j beta plus magnitude of k e to the minus j theta over, and there's a plus sign here, lose it there, over s plus alpha plus j beta. And what we've then demonstrated and pointed out is that this, in the complex Laplace domain, corresponds to, in the frequency domain, 2 times the magnitude of k e to the minus alpha t cosine of beta t plus theta, where in our current example alpha is equal to 3, so it's e to the minus alpha t. Beta is equal to, in this case, 4, and then theta is the angle associated with the positive root, or this term here. In this case, it equals negative j 53.13. So what we're saying is that when we can recognize that these two terms come as conjugates of this form here, we simply identify the magnitude of k, the angle of theta being the angle associated with a positive root, and then the exponential decay term here is the real part of this complex number down here, and the frequency of oscillation is the imaginary part. Thus, we get it into that form, we can just go directly to this, where it then becomes 2 times the magnitude of k e to the minus alpha t cosine of beta t plus theta.